everybody. So I think you already know about us. It's HackYour course AP and IB tutoring service. We are Canada's premier IB and AP tutoring service. And so today I've already introduced Peter and myself to you guys. So I'm not going to waste your time with that. We are going to move to our workshop. Don't forget, if you have any questions, just drop it in Q&A. I'm gonna raise it with Peter when he finishes that question, okay? And you need to be engaged. And also we are going to have polls for multiple choice questions, but any questions, ask it. If I can't transfer it very well, so we can turn on your audio to be able to ask directly in here yourself if you are fine with that, okay? And at the end, you are going to receive feedback. So give your feedback, and we are going to give away $50 Amazon gift card for the best and most constructive feedback. Okay, thank you, everybody. Let's get started. Peter?
Yes, I'm ready.
Let's go.
Okay, welcome everyone to the Chemistry IB 11 workshop. What I propose to do is to go through the first 5 topics in the chemistry course, emphasizing certain aspects, particularly things that have caused my students some difficulty. And as Masood said, should you have any questions, please don't hesitate to ask. So the first topic, as you know, is stoichiometry in the mole, which involves these topics, namely the calculations. And I will show you the 4 steps that you should follow whenever you're doing a stoichiometric calculation. It assumes you're capable of writing and balancing equations. That I will not be touching on specifically. Then, of course, you have to be familiar with the mole concept. What do we mean by a mole? 6.02 times 10 to the 23rd of anything is a mole. Then we will take a look at empirical and molecular formula determination, problems involving the limiting reagent, but we will not specifically look at theoretical and experimental yields because that will be covered when we do limiting reagents. And then I will point out some things that you need to keep an eye on when you're using the ideal gas law. All right, so those are the subsets of topic number 1. All right, let's move on. The most common question that I hear when we deal with stoichiometry calculations is, I don't know where to begin. I don't know what to do. My recommendation is that when you do these calculations, you follow these 4 simple steps. Namely, step number 1, you write the balanced chemical equation for the process that you're looking at. Now, oftentimes that is given, but if it's not given, it's imperative that you write it and you balance it. Then, once you've written the equation, then you take all the given data and convert everything into moles, all the chemical entities. And here I've summarized for you how you do these conversions. So for atoms, you take the weight of the species and divide it by the atomic weight. For atom ratios, when you're calculating empirical formulae, you divide the percentage composition by the atomic weight. For gases, you use the ideal gas law, PV is equal to nRT. For pure solids, liquids, and gases, you simply take the weight of the species and divide it by the molecular weight, or the molecular mass if you prefer. And then for any dissolved species, N will be equal to the concentration in moles per liter, or as you guys have to know, decameters cubed, times the volume in liters or decameters cubed. Right, so you've written the equation, you converted the amounts of all the chemical entities into moles, then you're ready to do all the required calculations using these moles as quantities. So whatever the question asks, you perform that calculation in moles, and then once you've performed it, you then convert your final answer, which will be in moles, into whatever units are requested in the question. Okay, so let me go through this again. As I say, this causes enormous difficulty for some of my students. balanced equation. Everything converted into moles, do the calculations in moles, and then finally convert your final answer into whatever is requested in the question. And I will do an example of this for you in a few moments. The ideal gas equation comes up when you're dealing with gases. And the thing that I want to point out about it is the units that you have to use to get the right answer. PV is equal to nRT, and you can replace the N by the weight divided by the molecular weight of the gas. The thing that confuses most people is that they use the wrong combination of units for pressure and volume. If you look in the Oxford textbook, they prefer you to use pascals for pressure and the volume in meters cubed. I find meters cubed an unhelpful volume. I'm not all that thrilled with decameters cubed either, but at least I can relate to liters. So you always use the pressure in kilopascals, the volume in liters or decameters cubed. That's the required combination. If you don't use that, you're going to be off by a factor of 10 to the 6th. The number of moles, of course, the ideal gas constant. This will be given to you on your data booklet. The absolute temperature, of course, has to be used, which is the Celsius plus 273.15, the weight in grams, and the molecular weight, either the molecular mass in grams or the relative molecular mass, which has no units because it's related to carbon-12. Okay? All right, let me illustrate. So here's my first sample problem to illustrate these points that we've been talking about. The reaction involving copper oxide with copper sulfide to produce elemental copper and sulfur dioxide. So in this particular case, they tell you that you mix 10 kilograms of oxide with 5 kilograms of sulfide, and you heat it until no further reaction occurs. The first thing you have to check when you encounter one of these questions is one or the other a limiting reagent? You cannot assume that the amounts that they give you will be of the correct stoichiometry. So the first thing you then have to do is to convert the given data into moles. So if I want the number of moles of copper oxide, I will just move this up a little bit so I have a bit more room to write. There we are. The number of moles of copper oxide will be down here. Whoops, that's a very thick pen. I apologize for that. We'll knock it down to 3. Hopefully this will be better. That's still, well, that should do. NCU2O is then the weight of the copper oxide, which is 10 to the 10 to the 3rd in grams, divided by the molecular weight of copper oxide. I assume you all know how to do that. That's 143.1 grams, and that works out to a ratio of 69.9 moles. You do the same thing for the number of moles of copper sulfide. In this case now it's 5 times 10^3 to the cubed grams divided by its molecular weight, which is 159.16. And that gives you the number of moles of copper sulfide, 31.4. So then you compare, is this the stoichiometric ratio or is one or the other in excess? Well, if you have 31.4 moles of copper sulfide, the balanced equation tells you you need twice the number of moles of copper oxide, which would be 62.8 moles. Clearly, the copper oxide is in excess, and so the copper sulfide is limiting. I know some of you guys aren't particularly adept at doing math in your head, so while you're checking this out in your calculator, that's the way you approach it. You check to see the ratio, and in this case, copper sulfide is limiting. So then the next question asks you, how much copper will be formed by using these reactants? So you go back to the balanced equation again, and you look at this, and you realize that 1 mole of copper sulfide will produce 6 moles of copper. Well, you know you got 31.4 moles of copper sulfide, so the number of moles of copper then will be 6 times that. So the number of moles of copper, which I'll write down here, N of copper, will be 6 times 31.4, which works out to be 188. And that's moles. So then they want the maximum mass of this. So therefore, you have to convert this now. This is the molar result of the final calculation. You have to convert it to grams. So therefore, you want to multiply this by the molecular weight of copper, the atomic weight, which is 63.55 grams per mole. So you do the conversion, so the mole units cancel, and the final answer then is 188 times 63.55, which turns out to be 1977 grams. Did I get that right? That can't be right. Sorry, it's 11,977. That's my sloppy handwriting. Okay, so that's the way you do it. You do the calculation in moles, and then you convert the final molar answer into whatever quantity is asked for. The second example is how to determine the empirical formula based on analytical data. And as I showed you at the very beginning, the way you do this is you take the percentage compositions and divide them by the atomic weights of each of these. So in this particular case, if carbon is 54.5, it's 54.5. Now you could go all the decimal places. I'm just going to divide it by 12. Hydrogen is 9.1%. I would divide that by 1, which leaves me oxygen at 36.4, because the whole thing has to be 100. And I'll divide that by 16. And if I do the math correctly, I end up with carbon 4.54. Hydrogen, of course, is simply going to be 9.1. And the oxygen is going to be 2.27. So therefore, you then let the smallest one be equal to 1, and you find out the ratio of the others to that. The carbon turns out to be 2. The hydrogen is 4. So therefore, the empirical formula of this compound is C2H4O. Okay, percentage composition divided by the atomic weights gives you this, and then you determine the ratio of the atoms by simply setting the smallest number equal to 1, and then find out the ratio relative to the other two. The molecular formula will be some simple multiple of the empirical formula, right? It's going to be once, twice, 3 times, etc. And usually they give you the data in order to calculate that. So in this particular case, I chose a situation where A is a gas, for which you have to use the ideal gas law, which I showed you earlier. So therefore you can plug in PV is equal to weight over molecular weight times RT. So molecular weight will then equal to weight over RT divided by PV. And if you put in all the numbers, as I indicated, this is already in kilopascals. The volume is in decameters cubed, so you just simply slap in the numbers, and you end up determining the molecular weight is 87.8. That's the relative molecular mass. So it has no units because it's relative to carbon 12. So we know the empirical formula is C2H4O. the molecular mass of the empirical formula, 24 plus 4 is 28 plus 16 is 44. Simply adding the atomic weights of 2 carbons, 4 hydrogens, and 1 oxygen. The empirical formula has a relative mass of 44. The authentic molecular mass is 87.8 or 88. So therefore, clearly, the molecular formula compound will be twice the empirical formula, and that's going to be C4H8O2. And that brings us to the end of the presentation regarding stoichiometric calculations. Are there any questions at this point before I move on to atomic structure? Everybody says, no, it was perfectly clear, wonderfully presented.
It seems so, right?
Or they're too shy to talk.
Well, hopefully not.
Which is
So
the,
any questions? You can put it in Q&A, and if needed, we can turn on the voice for you if you have any questions. I mean, why C4H8O2, if you understood, or nothing? You can raise your hand also if you like. Seems that everybody is fine, so.
All right, good
Okay,
to hear. Let's move on. Topic number 2 is atomic structure. The nuclear atom, the nuclear symbol, that's something that causes some people a bit of consternation. Remember, the nuclear symbol is Z, X, A, where Z is the atomic number, X is the element symbol, and A is the mass number. And some people tend to get confused and think that the mass number is the mass. It is not. All right, it's simply the number of protons and neutrons in the nucleus. And Z, of course, indicates the number of protons and electrons in a particular atom. All right, then of course you have to worry about isotopes, the mass spectra, electron configuration, Bohr's theory, all this, orbital shapes, and writing electron configurations in the periodic table. You will always have a periodic table handy. That's a very useful guide to keep track of things as atomic structure changes, and particularly useful for topic number 3 of periodicity, when you have to know the trends.
Sorry to interrupt. I've already put a periodic table in the chat for everybody. They can download it if they like. Click to open. The first one is the periodic table. Because Peter is going to ask you guys some questions, you need to have the periodic table. So you can download it from there and answer the questions. So we know if you are right or not. Okay, thank you. Sorry about that. Go on.
No, that's good, because I'm going to show periodic table as well. All right, so to get you involved directly, I have a few multiple choice questions to start with. Here's the first one. Which statements are correct for the emission spectrum of the hydrogen atom? Basically, that was the experimental evidence that we had that showed that the energies of electrons in an atom are quantized, that they can only have certain discrete energy levels. So do the lines converge at lower energies? Are the transitions to the ground state n equals 1 responsible for the lines we see in the UV region? And are these lines produced when electrons move from higher to lower energy levels? So we have it set up so that you can cast your ballot. So we'll see how you handle this question. Host and panelists cannot vote. Okay, I won't vote. All right. 57% said C, which is the correct answer. B, unfortunately, is not correct. Let me explain why. So do I close this or will you close this, Masood? Do I just shut this down?
I close it. If it hasn't
Okay, I just
closed for
closed
you,
it. Okay.
yes, you should close it yourself.
Yeah, 2 and 3 are correct. And in fact, one of the variants they sometimes ask on the exam is which lines are responsible for the ones that we see in the visible region? And the answer is those are the transitions to n is equal to 2, which is called the Balmer series. But the lines converge at higher energies. If you look at the picture in the textbook, the energy levels get closer and closer the farther away it gets from the nucleus. And so statement number 1 is incorrect. And of course, the lines are produced by transitions from higher to lower energy. That's why emission rather than absorption. Okay, inspired by that success, we have, this is not going to fit on the screen here. So do I want to make this smaller so everybody can see it? I think I should, eh? Yeah. Okay, here are 4 different atoms. They're neutron and proton compositions. And the question I ask is, which 2 atoms are isotopes? Everybody got it right. Good work, team. Right? Because, of course, you're looking for the ones that have the same number of protons, because isotopes simply differ in the number of neutrons. Remember, isotopes have the same chemical properties, but different physical properties. Very well done. All right, here's where you're going to need your periodic table. The electron configuration of vanadium. Okay, unfortunately, everybody missed this one. So clearly we better spend a little bit of time deciphering how we get electron configurations. The correct answer is B, but let's see how we arrived at that. And for that, I'm going to call up the periodic chart. So I go to New Share, and I call up my old periodic table. Here we are. Vanadium sits here. So therefore, the other way you could write the electron configuration for vanadium is by starting off with square brackets argon to indicate that you've got the configuration of argon. And then you will add the 2 s electrons. And remember, this is n is equal to 1, 2, 3, 4. So this is a 4s1, 4s2, then 3d1, 3d2, 3d3. But remember, as you go into the transition series, the level of the d electron energies drops below that of the 4s. So the correct configuration for vanadium is the argon configuration 3d3, 4s2. And of course, you can use the periodic table to decipher the electron configuration of any element, keeping in mind Hund's rule and the Pauli exclusion principle. Hund's rule says you keep electrons unpaired as long as possible. The Pauli exclusion principle says you can't have any 2 electrons with the same 4 quantum numbers. And so the other way you could represent this is, of course, with the arrows in boxes. Okay? So there's a couple of points I want to make about this. Namely, if the vanadium is 3d3, 4s2, which is answer B, then you would expect chromium, the element sitting next to it, to be 3d4, 4s2. Unfortunately, God didn't make it that way. Instead, chromium is a 3d5, 4s1. And they love to ask that because that's the exception to the rule. And that's attributed to the fact that you have less than a filled, you have a half-filled D shell. I'll write this out when I get back to the other side. The other exception to the rule is copper, all the way down here at element number 29, which, if you followed along, you think would be a 3d9, 4s2. Because you're down here, you have 9 electrons here in the blue, the transition metals, and the 4s. Again, copper is a 3d10, 4s1, attributed to the stability of the filled D shell. All right, so I'll go back to the question. Come on, there you are. Right, so the thing to note here is the correct answer is B, which can be written, as I say, as the argon configuration, 3d3, 4s2. Then the exceptions to the rule, next to vanadium is chromium, which, oops, why I got that? There will be argon. So this is chromium, is argon 3d5, 4s1. And the copper, which is argon 3d10, 4s1. Okay, and those last two you just sort of have to memorize. They are the exceptions to the rule. The final point that I want to make about electron configurations of transition metals is when they are ionized, when they lose electrons, they lose the s electrons first, right? There's a tendency to think, well, since in building up their configuration, I put the d electrons in last, therefore the d electrons will be lost first. That's not true. So in the case of vanadium, vanadium 2+, and sometimes they ask you for the ion, vanadium 2+ is simply the argon 3d3 with 3 unpaired electrons. Because remember, you have 5 d orbitals. Okay, similarly for the chromium, chromium 1 is a 3d5. Similarly, copper 1 is a 3d10. So remember that the d level energy is below that of the s, and that's true of the transition metals. The special cases are chromium and copper. And when you ionize a transition element, you lose the s electrons first. Okay? All right. It's strange because I can't see your faces, so I can't see if you're frowning at me, if you're smiling and nodding, if you're saying, what's he going on about there anyway? All right. Here's a favorite question from exams. What's the correct sequence for the processes occurring in a mass spectrometer? And sometimes they ask you to draw the picture of the mass spectrometer as it appears in the textbook. Here comes the vote. And the vote is no vote. Everybody is abstaining from this one. They say, we're not supposed to know the mass spectrometer. Why are you asking this question? All of these questions, by the way, come from old exams, right? Which I like to use with my students when we're preparing for the exam. And as I say, these are the ones that have caused some difficulty. So I'm focusing particular attention on these questions. Everybody's too shy to vote.
So should I relaunch it or you're going to explain it? So what's the process?
Is the system not working for some reason?
No, it seems that nobody knows. that's a problem.
Okay, then everybody says, I don't know, and I will explain.
Well, yeah, it's just they didn't write anything, so I think they don't know.
Okay, can you see their faces? Do they agree?
No, not unfortunately.
Okay. If you don't know, just vote A then. Yeah, no, I'm just teasing you. Okay, well, we'll close this.
Thank you.
The correct answer is, in fact, A. Because remember, in the mass spectrometer, first of all, you have to vaporize the sample. And so you can heat it, whatever. Then once you vaporized it, you ionize it. You kick electrons off it with an electron beam. Therefore, that will form a cation. Then that cation is accelerated through a magnetic field so that the things then separate based on their mass to charge ratios. And then they get deflected to the detector where they then get spread out in terms of mass to charge ratio. And the thing that you hope to get from a mass spectrometer is some indication as to the molecular weight of the particular species that you're looking at. And that's in fact how they establish the isotopic ratios of the various elements, by simply vaporizing an element and then simply putting it through the mass spectrometer to see how many isotopes it has. So the correct answer for this question is A. Now, we've lost Masood. I just see the company logo, so I'll carry on. So this data from the mass spectrometer can be used to calculate things, or we can reverse the process. If you look at your periodic tables, the relative atomic mass of chlorine is 35.45. And an often asked question is, okay, there are two isotopes of chlorine, chlorine 35 and chlorine 37. What must be their relative amounts in order to produce a relative atomic mass of 35.45 for the element. And you do all of these questions the same way. So in this particular case, you know that the relative atomic mass is 35.45. 35.45. And then you arbitrarily let one of the isotopes be X, the other will be 100 minus X. So let's say for the sake of argument, I choose the one having mass number 35 to be X. So that's going to be 35 times X. To that, I will then add 37 times 100 minus X. And the whole thing will then be divided by 100 because I want the percentage composition in the end. And if you solve this equation, what you find is that X turns out to be 77.5%. So therefore, that is the abundance of 35 chlorine. And 100 minus X, therefore, is 22.5%. And that, therefore, must be the abundance of 37 chlorine. Which makes sense because the mass, the relative atomic mass is closer to the 35 value than the 37 value. So clearly, you must have more of the 35 chlorine isotope than you have of the 37 chlorine isotope. Okay? So as I say, you can punch the numbers into this and work them out, and this is what you will find. A very commonly asked question. Okay, now if I could see Masood, I would say we've reached the end of topic number 2. So we're ready for any questions.
Nothing from moles. I think if you guys have any other questions from moles, I think Peter can easily answer that.
Or any of the things, I mean, orbital shapes. Do you know your orbital shapes? You have to know what the s orbitals look like and the p orbitals look like.
It seems that, and by the way, the question and answer is anonymous, so don't worry with your friends to figure it out. That you are here. So it seems that nobody has any questions. They're very good.
Any questions. Now they're either completely confused or they find this trivial and they're saying, when are we going to get to the tough stuff, eh?
God knows. Well,
we can't see your faces, so we don't know what your reaction is.
And I think they shied it.
Remind them of orbital shapes. Do you remember orbital shapes? S orbitals are completely spherical. Oh, that's a lovely sphere, not bad. P orbitals are along the axes, and they have a dumbbell shape. So they look like this. Well, the two sides are supposed to be the same. And so they're along the axes. So the px orbital is along the x-axis in your usual Cartesian coordinate system. Py is along y, and pz is along z. And remember, in the quantum mechanical model of the atom, there's something called the Heisenberg uncertainty principle, which says if you know where the electron is, you really don't know what it's doing there. And if you know what the electron is doing, you don't have a clue where it's doing it. And so the best way to look at orbitals is that they represent the probability of finding a particular electron. So s electrons have the same probability in all directions because they're spherical, situated around the nucleus. The p electrons, on the other hand, have specific regions where they are most likely to be found, namely along the axes. Okay, this is strange. I'm not used to teaching without seeing some reaction from the people I'm talking to. But it's a new experience for all of us. Okay, I think that's about it. Is there anything else there? Should have remembered Bohr's theory. As I say, Bohr's theory just introduced the idea of quantization. Isotopes, writing configurations. Okay, I think we've covered it. So then, once you've developed the electron configurations, you can then start looking at the trends in the periodic properties of the various elements. And that's essentially what topic number 3 deals with, periodicity. The periodic table, where you have to be able to recognize metals, non-metals, and metalloids. The periodic trends and radii, ionization energy, electron affinity, electronegativity, trends in metallic and non-metallic character. And then they always have a descriptive section on the chemical properties of the alkaline metals and the halogens. Those are simply selected as 2 representative groups, and you pretty well sort of have to know that or be able to reason it out, because they tend to ask about it, and I'll ask you about that as well. But first, I'm going to go back to my periodic table, which is here, and point out what have we got. I like this colored table because it separates things very clearly. The metals are to the left of the periodic table. And so the group 1 elements are called the alkaline metals. The group 2 elements are the alkaline earth metals. The transition metals, the guys in blue, are here in the middle. Then you're sort of in no man's land, where these orange colored species are basic type metals, so they will form bases, and they're separated from the non-metals. The non-metals are the ones up here on the right-hand side. They're separated by these green elements, indicated in green, which are, they label them here as semi-metals. These are also called the metalloids or semiconductors, which means that they have properties intermediate to metals and non-metals. So they might appear as a metal, they have a nice shiny surface, but their chemistry is dominated by their tendency to acquire electrons rather than lose electrons. Then up here in the blue, these are the clear non-metals, as are the halogens, group 17 or 7, however you choose to label it, and of course the noble gases. So the chemical trends, as you may have seen, electrons tend to be lost from metals. So the alkalis very much want to lose their 1s electron and form a positive cation. Similarly, the alkaline earths want to lose both s electrons and form the 2+ cations. Conversely, at the other end of the spectrum over here on the right-hand side, the halogens all want to gain an electron to get to the noble gas configuration. And these smaller ones up here like to do the same. So oxygen likes to pick up 2 electrons to form oxide, nitrogen 3 to form nitride, and so on. And that's the driving trend. Excuse me. The metals are losing the electrons to get to the noble gas configuration. The non-metals are gaining electrons to get to the noble gas configuration. Okay? So what are the trends? Well, first of all, there's a trend in size. The trend in size is it always increases down a group. And that's simply because you're going to higher and higher quantum shells as you introduce electrons into the elements. So for example, cesium down here is in a 1, 2, 3, 4, 5, 6s electron, which is way the heck farther out than lithium with its 2s electron. So the atomic radius of cesium is markedly bigger than that of lithium. And that's true of all the families in the periodic table. If you go down group 3, group 4, and so on down the line, things get bigger as you go down. The other trend for size, as you go left to right across a period, the size diminishes. And so, for example, as you go from lithium to neon, the size keeps getting smaller as you go across, simply because as you're adding electrons and building up the electron configurations of the elements, you're also adding protons to the nucleus. And that means there's a greater positive charge on the nucleus that's holding the electrons more tightly. So therefore, the trends in size increases down and diminishes as you go to the right. So in other words, the biggest elements are down here in the lower left corner. The smallest elements are in the upper right-hand corner. Okay? Size increases as you go down and as you go to the left. Well, that's also then reflected in some of their physical properties, not only in terms of their radii, but also in terms of their ionization energies. Namely, electrons that are sitting further away from the nucleus can be lost more readily than ones that are close to the nucleus. So the ionization energy of cesium is a heck of a lot lower than that of lithium, because cesium is losing a 6s electron, which is far removed from the nucleus, as opposed to lithium, which has a 2s electron, which is fairly close to the nucleus. So therefore, ionization energy runs similar to the size. As things get bigger, the ionization energy goes down. So the group trend then is ionization energy goes up as you go up a group, or it decreases as you go down. Similarly, we know the size diminishes as you go to the right. So therefore, ionization energy will increase as you go to the right, because again, the smaller guys are holding the electrons more tightly. So therefore, the trend in ionization energies increases to the right and increases as you go up. And so fluorine is hanging on to its electrons very tightly. Cesium and francium say, ah, here, have an electron. Okay? That same trend is then also reflected in electron affinity, because the tendency of the nonmetals to acquire electrons is much greater than that of the alkalis. And remember, the electron affinity is a gaseous atom, neutral atom, acquiring an electron to form an ion. And so that trend again manifests the size factor. And we'll talk about electronegativity a bit later when we talk about bonding. Okay, so I can go back to the questions here. Ionization energy, we pointed out where the metals, the non-metals, and the metalloids are. The trends in the radii, the sizes, ionization energy, and electron affinity. We'll deal with electronegativity a bit later, and we'll look at the periodic trends in metallic and non-metallic character as we go through this topic. So here we have the first sample problem concerning the properties of the elements. Now note, this question is asking specifically about non-metals. Right? It's not asking for the trend all the way across from sodium to argon. It's specifically asking what are typical properties of the non-metals in that period. And again, everybody is too shy to vote. Okay, so again, we have no response.
No response.
We have no idea if anybody is understanding anything that I'm going on about. How about if you vote D to indicate that you at least understand what I'm talking about?
Okay, I'm gonna do it again. Let's go.
Okay.
A,
This is just to answer the question. Are you understanding what I'm talking about? Or are you completely blown away? If you understand, please vote D.
if you don't understand or understand.
If you don't understand, don't vote. So if it's a complete blank, that means nobody understands what I'm babbling about.
Okay.
I want to
Let's
see
see.
how many people have a clue of what I'm talking about.
Okay, so if you understand, vote D. If you don't vote.
Yeah. So if it comes back all blank, that means nobody understands what's going on.
Okay. So it seems that everybody
Thank you very
understands.
much. Everybody understands.
Well,
Good.
everybody who voted understands. I think we have a few people who don't understand, but the majority understands.
Okay. That's a good sign. So
That's a
then
good sign.
what is the correct answer to this question?
Nobody knows.
Well, let's review what I just told you. These are the non-metals in period 3. So these are the guys on the right-hand side. They form ions by gaining one or more electrons. Let's remind you of the periodic table. So we're talking about these guys over here. What's their tendency? Their tendency is to acquire electrons to get to the noble gas configuration. So that statement seems to be true, one would think. They are poor conductors of heat and electricity. Remember, to be conductors of heat or electricity, you have to either have mobile electrons or mobile ions. Well, the non-metals sitting over there on the right-hand side have neither. So they are poor conductors of heat and electricity. Do they have high melting points? No, they do not, because as we'll see in the next topic, they like to form nice covalent bonds with intermolecular forces that are not all that strong. So the correct answer to this question is A, 1 and 2 only. Yes, the nonmetals form cations by picking up electrons, and yes, they are poor conductors of heat and electricity. Whereas metals, on the other hand, do conduct heat and electricity quite readily, as we shall shortly see. All right. So if you understand what I was babbling about, then this one should now be, now you're comparing both the alkalis and the halogens. And we want to know which of the physical properties decrease with increasing atomic number. So you're going down the group. So we have a split vote. And it turns out that B, in fact, is the correct answer. A and D are incorrect. Let's take a look why that is. we want a property that decreases with increasing atomic number. Well, as I just showed you, if you go down a group, things get bigger. So the atomic radius gets bigger, it does not decrease. The ionization energy does decrease because the electrons are getting further and further away. So 2 is a yes. Melting point, now you have to be careful about this because the interatomic forces between the alkalis and the halogens are different. The alkali metals have metallic bonding. Remember, metallic bonding involves cationic metals, the cations of the metals, in a sea of delocalized electrons. Whereas for the halogens, they're nice diatomic molecules with only London forces acting between them. And so for the alkaline metals, the melting point would probably diminish because you're in a situation where as you go down to the bigger metals, they're not holding on to the electrons as tightly, and so they can melt more readily. The halogens, on the other hand, the London forces increase as you go down because something like iodine has a heck of a lot more electrons in it, and so there are more London forces. So that trend is not true for both groups, and we'll see some of that a bit later. So here, the only thing that decreases with increasing atomic number for both the metals and the nonmetals is ionization energy. And as I say, we'll talk about metallic bonding and the halogens a bit later when we talk about bonding. All right. Now we want the series arranged in order of increasing radius. All right, we're evenly split. The correct answer is C. And let me show you why. If I go back to the periodic table, we're talking about calcium 2 plus, potassium plus, and chlorine minus. All three of them have the argon electron configuration. All right, that was the first thing you have to recognize. So then their size will be determined by their nuclear charge. Clearly, the charge on calcium, nuclear charge, is greater than that on potassium, is greater than that on chlorine. Because chlorine only has 17 protons, potassium has 19, calcium has 20. So therefore, the Cl minus will be the bigger than the potassium, than the calcium. Go back to here. So C is the correct answer, right? Simply because they all have the same electron configuration, the argon configuration, but chlorine has fewer protons than does potassium, than does calcium. And so the calcium will be holding its electrons more tightly, hence it'll be smaller. Okay. This I put on because people tend to get electronegativity confused with electron affinity. Electronegativity, as defined by Linus Pauling, is the power of an atom in a molecule to attract electrons to itself. Right? It has to be in a molecule. So what we're talking about is if we have a bond between two atoms, A and B, the electrons will not be shared equally because A and B will have different electronegativities. They will only be shared equally if you have the two electrons shared by the same atom. Like in the halogens, for example, if this is chlorine-chlorine, the two electrons will be shared equally by the two chlorine atoms in Cl2. In any other one or another of these will have the electron spending more time around it simply because it has a greater electronegativity. So if I suppose that B is more electronegative than A, then I should correctly represent the two bonding electrons as closer to B, and the A therefore will have a slightly positive charge, delta plus, and the B will be a slightly negative charge, delta minus. And so the bond between A and B will be polar. So if I go back to the periodic table, electronegativity increases to the right and up. So the most electronegative element known to peoplekind is fluorine. And that gets assigned an arbitrary value of 4. There is a chart in the Oxford textbook that shows you the electronegativities of all the elements. But again, you see the electronegativity correlates with size. Namely, the small guys want the electrons more. Remember, size diminishes as you go to the right, and as you go up, that's the same trend with electronegativity. All right, back to this question. So the key point about electronegativity is the attraction of electrons by an atom in a bond or in a molecule. It's not the naked atom attracting electron from outside. So why then are the noble gases not assigned electronegativity values? This is a bit of a trick question. You have to think about it a bit. The answer is simply because the noble gases don't form that many compounds. So we don't have that many systems from which to get the data. Right? There simply aren't that many noble gas compounds in order to enable us to categorize their electronegativities. That's a favorite question that gets asked on exams quite a bit. How come the noble gases don't have values? All right. Oh, well, I just answered my own question here. The trend in electronegativity across period 3 from sodium to chlorine. Electronegativity increases as you go to the right, simply because the number of protons increases, and so the nuclear charge increases as you go to the right. And so therefore, as you go to the right, in this, I'll put this up again, the periodic table, the bonds involving carbon, nitrogen, oxygen, and fluorine all become polarized with the C, N, O, and F being delta minus. Right? Classic non-metallic behavior. Okay. So then, to finish off this particular topic, I asked the question, why does chlorine, rather than bromine, react more vigorously with a solution of I minus? So you have to think about where we are in the periodic table. Chlorine sits above bromine. The general reaction, and I'll illustrate this for the chlorine, is Cl2 reacts with 2I minus to form I2 plus 2Cl minus. In other words, the chlorine wins the battle for the electrons. And so the iodide loses electrons, the chlorine picks it up. And that's simply because on the periodic table, as you go down the halogens, you have fluorine, chlorine, bromine, and iodine. Electronegativity increases as you go to the right. And so therefore, chlorine wants the electrons more than the iodine, and hence this reaction occurs. It reacts more vigorously with bromine because bromine is less electronegative than chlorine. And so the reaction with bromine takes a little longer. Next year, you will see that this is called oxidation and reduction, redox, which is in a later chapter of the book, but you don't have to worry about that now. Okay. And then the last one, this is what I call a straight regeneration of facts that are given in the textbook. There's no way you can decipher this. You just simply have to know it. And what you have to know is the metallic oxides are basic, non-metallic oxides are acidic, and aluminum right in the middle is amphoteric, which means it can react both as an acid and as a base. Okay, so metal oxides are basic. Non-metal oxides are acidic, and the aluminum sits right in the middle. If you remember your periodic table, should I drag that up again? Here's aluminum sitting right dead center between metals and non-metals. So the metals will all form basic oxides, the non-metals form acidic oxides. The aluminum oxide can react both ways. It's amphoteric. So we go back to this here. Al2O3 is amphoteric. So then the question asks to write the equations to demonstrate the acid-base properties. These you can find on page 86 and 87 of the Oxford textbook. The basic point is metal oxides will form metal hydroxides. So the magnesium will form MgOH2, metal hydroxide. The P4O6 will form an acid. It can either be phosphoric acid, but more common is H3PO3 for the phosphorus. As I say, the equations for this are in the textbook. And then they'll give you the equations for the aluminum oxide. It can form both types of species, right? But the trend to remember is metal oxides, non-metal oxides, and aluminum in the middle. Very commonly asked question. As I say, you pretty well have to memorize that because you can't decipher it just by first principles. And I think if I remember correctly, that completes topic number 3, and we get into the big topic, bonding.
Well, I still don't see any questions.
Bonding, we will ask the usual question. Does the silent audience have any questions?
No, it seems that they are either the teachers or the competitors.
They're saying, boy, he's throwing this stuff at us so fast, we can't possibly figure this out.
I don't know. Nobody is asking. Everything is clear. If everything is clear in topic 3,
well, we will find out on the evaluations afterwards when they'll say, I never heard anything more confusing in my life. And I'm taking this course.
Yeah, let's see. Well, nothing yet. So everybody is clean then. Let's move on.
Okay, so bonding, as you can see, is a major topic dealing with ionic, covalent, Lewis electron dot structures, VSEPR, bond angles, all that good stuff. And again, there's topics in this chapter that you just simply have to know, namely the covalent network solids. So let's go through them with some typical questions, and I'll discuss each of the points as we encounter them. So here's the first one. What does VSEPR theory predict? So this one you have to know. If you don't answer this, I hang up my shingle. Here comes the final answer, and everybody missed it. The correct answer is B, the shapes of molecules and ions. VSEPR has nothing to do with the energy levels, and it has nothing to do with the electronegativity. VSEPR relies on you being able to draw the Lewis dot structure of a particular compound. And so let's, for the sake of argument, do ammonia. My approach in drawing Lewis dot structures is to simply count up the total number of valence electrons that you have, and then simply use them to connect the atoms. So you know that nitrogen has 5 valence electrons, each hydrogen has 1. So therefore you have a total of 8 valence electrons to put into this diagram. And so 2 each are used to form the nitrogen-hydrogen bonds. So you've got a lone pair sitting on the nitrogen. VSEPR enables you to predict the molecular shape, but can also tell you the electron domain geometry. Namely, if you look at the nitrogen atom in the middle of all of this, it has an electron domain of 4. Whoops, way too thick of an arrow. I'm going to keep going here. It has an electron domain of 4. I should make that a thinner line here. Come on, give me a 3. There we are. And a 4 electron domain means it's tetrahedral, symbolized by T sub D. And remember, a tetrahedron is joining alternate corners of a cube. So here's my cube. To get a tetrahedral array, I put 1 here, 1 here, 1 here, and 1 here, with the central nitrogen then sitting in the middle. But the electron domain geometry just tells you how the electrons are situated. It doesn't tell you about the molecular structure or the molecular geometry. That simply indicates the positions of the atoms. And so in the case of ammonia, you would then have the situation where I could put the 3 hydrogen atoms sitting here, here, and here. And the lone pair then would be sitting out here, and the nitrogen is in the middle of the cube. And so ammonia has a trigonal pyramidal structure, whereas its electron domain geometry is tetrahedral. So you have to make sure you differentiate the two. But VSEPR has nothing to do with energy levels, nothing to do with electronegativities, and it tells you nothing about the types of bonding. It just tells you where these atoms should be positioned if you have a situation where you can draw a Lewis dot structure. Okay? All right. So to test your ability to draw Lewis dot structures, in the next question I ask you, which molecule is nonpolar? And this could take a bit of time. We have a split between B and C. C, unfortunately, is like ammonia, right? That I drew up here, in which the hydrogens can be replaced by the fluorines. And so NF3 also has a trigonopyramidal structure. And remember, the way that you determine whether a molecule is polar or nonpolar is you apply the individual dipoles. So if I take NF3, for example, NF3 is trigonopyramidal this way. Then I can indicate individual bond dipoles for each nitrogen fluorine link. And it'll be this way because fluorine is more electronegative. And again, I forgot to thin the arrow. So the net dipole moment of NF3 will be an arrow extending down from the nitrogen between the fluorines. So the net dipole moment I'll indicate in what? In black. Was down here then, right? So NF3 is polar. And so those of you who voted for SO3 are absolutely correct. It's trigonoplanar and it does not have a dipole moment. The other guys do. Okay. Which statement is true for most ionic compounds? And unfortunately, everybody missed this one. The correct answer is D. Well, you didn't vote for A, which is good, because of course to be ionic, they wouldn't have similar electronegativity. You're going to get an ionic compound formed, but you combine an electropositive element like sodium with an electronegative element like chlorine to form Na plus Cl minus. But they can't conduct electricity in the solid state because in an ionic lattice, whoops, I keep switching colors and I keep forgetting to thin out the thickness of the pen here. Let's make it a 2. In the solid state, of course, you have the ions, like something like sodium chloride, sitting in a rigid lattice. It's a cube. You may have seen the picture in the textbook. If the ions cannot move, they cannot conduct current. So ionic compounds do conduct current when they're molten, when the ions are mobile and they can move, but they cannot in the solid state because they're locked in to a rigid structure. Most ionic compounds are colorless. In fact, offhand, I can't think of simple ionic compounds that are colored. The key answer then is they have high melting and boiling points simply because the ionic forces, the electrostatic forces acting between oppositely charged ions are very strong. And so it requires a lot of energy to break apart that interaction, to then, in the first instance, to melt it. So try melting some salt at home. Ask your mom if you can do that. You'll see it takes quite a bit of heat to do that. And then, of course, it requires much more heat to convert them to the vapor. And plus, you don't want to be standing around inhaling sodium chloride vapor. So the correct answer is D. They have high melting and boiling points. And that's sort of going to set us up for intermolecular forces. So there's covalent bonding, ionic bonding, and then the intermolecular forces. And so on this multiple choice question, I ask you, which compound contains both ionic and covalent bonds? Unfortunately, magnesium chloride is ionic, HCl is covalent, H2CO is covalent. The one that contains both ionic and covalent bonds is NH4Cl. Because, let me go back to my blue pen here, that contains the ion NH4 plus, cation with Cl minus. And NH4 plus is exactly the same as CH4 because the nitrogen plus is the same configuration as carbon, and CH4 is tetrahedral. So there's covalent bonding in the NH4 plus ion, and there's ionic bonding between the cation and the anion. So the correct answer is D. All right. Here are compounds who have very similar molar masses. Which has the strongest intermolecular forces? And remember, the intermolecular forces are London forces, dipole-dipole forces, and hydrogen bonding. Well, I'm proud to say that 2 of you got it correct. B is the correct answer. C is close, but not quite. So let's just list what are the intermolecular forces in each of these compounds. For every compound that you encounter, you can automatically write London forces. Everybody has London forces. Oh, good Lord. We're going to let that ring. Sorry about that, guys. I can't shut it off. So this has London forces. This has London forces. This is London forces. This is London forces. D has nothing else. It only has London forces. This particular one, you do have a polar carbon-fluorine bond. So this will have dipole-dipole interactions. Here you have a polar carbon-oxygen, oxygen-hydrogen bond. So this will also have dipole-dipole interactions, as will this guy. But the thing that sets B apart is that it can have hydrogen bonding. Remember, hydrogen bonding has to have the hydrogen attached to a nitrogen, an oxygen, or a fluorine, because they're the most, whoops, this should be a high. So, Peter, you tourist. Where's my erase button here? Here we are. Whoops, I erased the whole thing. Shouldn't have done that. Let's go back. Okay. So this, I don't want to do that again. So this has to be a hydrogen. Whoops. Why do I keep doing that? Because I'm still on in my erase function. Okay, let me just change that. Move off my erase function and go to my write function. This has to be a hydrogen. That's hydrogen attached to the 3 most electronegative elements, which means that all of these guys in the left-hand column minus, the hydrogens become slightly delta plus. So they can then hydrogen bond to a species carrying a lone pair of electrons. So in the case of the OH here, this hydrogen can then hydrogen bond to an oxygen of another OH, etc. So D has only London forces. A and C have London and dipole-dipole, but B has London, dipole-dipole, and hydrogen bonding, which means it'll have the strongest intermolecular forces. Okay? All right. So here we have diagrams representing the structures of iodine, sodium, and sodium iodide. And so you have to identify which is which. This is not a multiple choice question. I will tell you the answers. A is sodium iodide, the classic ionic lattice. Notice in a cubic type array, arrangements of cations and anions with very strong electrostatic interactions between the ions. B is sodium, the metallic cations in a regular lattice array surrounded by a sea of delocalized electrons. And C is iodine, the diatomic molecule, only London forces interacting between each of the I2 molecules. The type of bonding, A is ionic, B is metallic, and C is intermolecular forces between the diatomic molecules. The bonding within each diatomic molecule, of course, is covalent. But in C, you only have van der Waals or London forces. That's it. So therefore, in terms of volatility, you would expect C to be the more volatile, the more readily vaporized. So here's the point that I was talking about before. Sodium and sodium iodide can both conduct electricity when molten, but only sodium can conduct electricity when it's solid. That's because sodium iodide, as a solid, is rigid. The ions can't move. So it's only when it melts and it forms discrete Na plus I minus ions in the melt that are mobile, then you can have current conducting. The sodium has conductivity because it's got a sea of electrons around it, and it will have that whether it's in the solid state or in the molten state. The electrons will always be there to conduct current. And the iodine, of course, is a non-conductor right from the word go. And the high volatility of iodine compared to sodium and sodium iodide, the iodine molecules are all held together by van der Waals or London forces, which are the weakest intermolecular forces. Sodium is held together by metallic bonding, which is stronger than London forces, and ionic bonding in sodium iodide is the strongest of all. So iodine by far will be most easily volatilized. Volatilization means you're converting it to a gas. And so in fact, if you see a sample of iodine in a jar, iodine is very sort of purple, you will notice there's always a bit of iodine vapor above it. It's fairly easily volatilized. Okay, and that completes topic number 4. And we're right on schedule. So I'm waiting for my leader to show up. Hello, leader. It's time for another. Do we have any questions? No, we have no questions. Let's move on.
We have no questions. Everybody knows everything, or they is
so
sleeping.
confused now. They're wondering why they ever took Chemistry 11 IB. Or why they should have gotten in touch with us sooner. Who knows? Okay, thermochemistry.
Oh, hold on a second.
Oh, we have a question?
Yeah, no questions. The question is no questions. Okay. Well, thank you for talking. There you go.
There you go.
You were missing the interaction, Peter. That's the interaction. Go, enjoy it.
I'm used to chatting with my students. I get a rapport.
Yeah, that's how you.
We exchange ideas freely.
Yeah, that's how you teach, right? So, but
exactly.
Hopefully, you'll have more questions.
The thing you have to remember, it only cares where you start and where you finish. It doesn't care how you get there. Because the thermochemistry involves a quantity called H, which is enthalpy. And at point A, it will have an enthalpy symbolized by H sub A. At B, it will have an enthalpy symbolized by H sub B. And if you make the transition from A to B, the change in enthalpy then will be given by HB minus HA. It doesn't matter if you take that path or if you take a path like this, wander around, as long as you end up at the same final point, the delta H will always be the same. Okay? So then you have to differentiate between endothermic and exothermic reactions. Endothermic means you have to supply heat to the system, or heat is taken from the surroundings. Exothermic means heat is given off to the surroundings. And there's a sign convention. If it's endothermic, the delta H is positive. I'll put that up here. That's plus delta H. If it's endothermic, it's negative delta H. The convention being that everything into a system is positive, everything out is negative. And then you can have enthalpies for different kinds of processes. The standard enthalpy change of formation, which refers to the making of a compound from its constituent elements under standard conditions. In which case, then, your delta H would be the sum of the H's of the reactants minus the sum of the H's of the products. There's also the enthalpy change accompanying combustion. Usually for organic type compounds, when you convert them from one state and you burn them in the presence of oxygen to carbon dioxide and water. Hess's law you use when you can construct a different path so you can calculate a delta H for something that you may not be able to measure directly otherwise. And then there's bond enthalpy, because you can use bond energies also to calculate delta H's by simply calculating the amount of energy spent to break all the bonds in the reactants, and then look back at the energy that you gain when you form the new bonds in the products. So therefore, let's start off with this multiple choice question. Speaking of bond energies, what energy changes occur when bonds are formed and broken? Unfortunately, you got it backwards. When bonds are formed, you have a situation in which energy is released. Just think in terms of if you're going to decompose a chemical compound, you're going to pump energy into it to break it apart, right? So therefore, the correct answer is D, because energy is absorbed when they're broken because you have to pump the energy into the system. It's released when the bonds are formed. You get the energy back. So then, here's a typical chemical process with the delta H0. That's the standard enthalpy change accompanying this reaction. If that data is given, which energy change then accompanies the formation of 1 mole of hydrogen? And everybody was afraid to vote. Okay, so what this equation tells you is that for this reaction, the enthalpy change is 210 kilojoules, and it's energy that is absorbed from the surroundings, right? It's endothermic. So the question then is, if you have 1 mole of hydrogen formed, what will happen? Well, you would then divide this equation through by 3. And correspondingly, you would then change the delta H naught value by dividing this by 3. And so the correct answer is A, 70 kilojoules of energy will be absorbed from the surroundings. Because enthalpy is a state function, but it does depend upon the equation as written. So if you multiply through by a coefficient, you have to multiply the delta H. If you divide through by a coefficient, you have to divide the delta H by the same coefficient. Okay, and then we will close today's session with a couple of computations that commonly occur in these sorts of questions. So, now this is a fairly lengthy question. Maybe I can make it a little bit smaller so you can see it better. All right. So this is a reaction between potassium hydroxide and hydrochloric acid to form potassium chloride and water. And this is an experiment conducted to determine the enthalpy change of this reaction. In other words, what is the delta H of this? And this is called the enthalpy of neutralization because KOH is a base and HCl is an acid. So they take 50 centimeters cubed of a half molar solution of KOH, and they mix it in a glass beaker with 50 centimeters cubed of a half molar solution of HCl. And they monitor the temperature. And what they find is that the initial temperature was 19.6 degrees, and it went up to 23.1 degrees. So the first question they ask is the reaction exothermic or endothermic? Hopefully, all of you are saying it's exothermic because the temperature went up, right? Had it been endothermic, the reaction mixture then would have cooled because it's taking heat from the surroundings. So here, this is an exothermic process. Exothermic. Okay. Then they want you to calculate the enthalpy change of this reaction in kilojoules per mole, assuming that the specific heat capacity of the solution is the same as that of water. All right, so whenever you have one of these where you're measuring the heat transferred, you always think of the standard equation. Q is equal to MC delta T, where heat then is the amount of heat. Q represents the amount of heat transferred, M is the mass, C is the heat capacity, and delta T is the change in temperature. So in this particular instance, you go back to the question, and I'm sorry this is a bit, I'm going to be jumping up and down here. I took 50 milliliters, I think in terms of milliliters rather than cubic centimeters. So I took 50 milliliters of the solution of KOH and 50 milliliters of the solution of HCl. So in the end, I ended up with 100 milliliters. And 100 milliliters of water weighs exactly 100 grams. So this here will be 100 grams. The heat capacity of water is in your data booklet. It's 4.18 joules per gram per Kelvin. And the change in temperature, we went from 19.6 to 23.1 is 3.5 K. And remember that the size of a Kelvin degree is exactly the same as that of a centigrade degree. So you don't have to change, right? This is a delta T. It's not an absolute T. So if you put all these numbers in there together, this turns out to be 1,463 joules, which is equal to 1.463 kilojoules. Okay? So then they want the enthalpy change of this reaction in kilojoules per mole. So then you then have to look at how many moles did you take of each of these. Now you notice in this particular case, we started off the discussion today by looking at limiting reagents. Here you're given exactly the correct amounts of reagents. So this is the stoichiometric ratio, right? You take 50 milliliters of a half molar KOH and 50 milliliters of half molar HCl. So you can then say, to calculate the number of moles, you're going to have essentially 0.050 0.050 this is now liters. And you're going to multiply that by the fact that it's 0.5 molar, 0.500 moles per liter. And this is true of both the HCl and the KOH. And so the net number of moles is 0.025 moles. In other words, in this reaction, you took 0.025 moles of KOH, combined it with 0.025 moles of HCl to form 0.025 moles of KCl and 0.025 moles of water. That's what the balanced equation means. So therefore, to get this now, you know that therefore 0.025 moles generated 1.463 kilojoules. So the delta H of this reaction then will be 1.463 kilojoules divided by 0.025 moles, which works out to be minus 58.5 kilojoules per mole. Right, so you calculate the heat first, then you calculate the amount of moles involved in the reaction. And as I say, you check to make sure that the stoichiometry is correct, which in this case it is. And so then you can say that the amount of heat that you measured was generated by 0.025 moles. So therefore, 1 mole will generate this amount of heat. And this is what you'd see tabulated for the reaction involving KOH with HCl as the heat of neutralization. Okay? So the final twist on this question is the experiment was repeated, but with an HCl concentration of 0.510 moles per decameter cubed, or 0.51 molar, instead of 0.5 molar. What temperature change will you then see? Right, so you're changing the experiment now. Instead of using 0.5 moles, you use 0.51 moles of HCl. And the answer is, it will make no difference whatsoever, simply because in this particular case, if you have more HCl, the KOH is still limiting. And the KOH hasn't changed, it's still 0.025 moles. So you'll have exactly the same amount of heat released. You'll simply have a little bit of HCl left over unreacted. Okay, so this is how we bring it all back to limiting reagent where we started the whole process. Okay, so therefore, in this particular answer here, no change. Simply because the KOH is limiting. All right, and the final question today is a Hess's law type calculation. And you see many of these questions where they'll give you some data and then they'll ask you to calculate something or other, okay? The best way to approach this is to say, all right, where they want to calculate the average bond enthalpy, what reaction are we talking about? And then you could recast the given data to come up with the final equation. So when we're talking about the average bond enthalpy for a CF bond, one plausible reaction would be C as a gas reacting with 4 fluorines as a gas, 4 fluoride atoms, I should say, as a gas, to form CF4 as a gas. Right? This is simply looking at the data that you're given. Because whenever you calculate bond enthalpies, you have to be calculating species in the gaseous phase. So this is the equation that you want, because the delta H for this corresponds to the breaking, or the formation in this case, of 4 carbon-fluorine bonds. So therefore, the average bond enthalpy of a carbon-fluorine bond will be this delta H divided by 4. So what you then look at is, all right, how do I recast the given data to come up with this as the final equation? And so the way you look at this, you say, well, I need to have carbon gas as a reactant on the left-hand side. I need fluorine gas as a reactant on the left-hand side. And I need CF4 as the product. So that tells me if I want carbon gas as the reactant, I can then flip the bottom equation around and write that carbon gas goes to carbon solid. And that will have a delta H3, because I've now flipped it around. It'll be minus 715 kilojoules per mole. I'm not going to worry about the units. Right? I've got to change the sign because I'm now doing the opposite of what is given. All right, I want 4 fluorine atoms on the left-hand side. So I can flip the second equation around, but I have to multiply it by 2. So then I would write 4 fluorines as a gas goes to 2F2, and the delta H2 in this case now not only has to be flipped around, but also has to be multiplied by 2. So it's minus 2 times 158 kilojoules per mole. The final one, I need to have CF4 as the product. Well, CF4 as a product is already in the first equation, so I don't have to change that. So CS plus 2F2 goes to CF4 as a gas. Oh, I should be writing gas here, sorry. This should be gas, and this should be gas, and this should be gas. That remains intact, and that has a delta H of minus 680. So if I've done this correctly, I can then eliminate things on both sides of the equation. So I can eliminate the carbon solid here. If I add, I'm now adding these 3 together. And I'm adding them up this way to produce that as the final equation. So clearly I can cancel carbon solid. It appears both on the left and on the right. Right? I need the carbon gas and the 4F gas to stay here. But now I can also eliminate the 2F2 in the product here and the 2F2 in the reactant over here. And in so doing, look what I've done. I left carbon gas reacting with 4 fluorine gas to give me CF4 as a gas. So therefore, if I add all of these numbers together, according to Hess's law, I will end up with the delta H for this reaction. And the delta H for this reaction, if you do that math, turns out to be minus 1711 kJs per mole. This is adding these numbers up that way. Minus 1711 kJs. So therefore, the final delta H that I want is minus 1711 divided by 4. Because I formed 4 carbon-fluorine bonds, so then each one will be minus 428 kJ per mole. And so if you look in your data booklet for the average bond enthalpy for a carbon-fluorine bond, you will find that number. And this is one way of computing it by simply using Hess's law to combine the different equations to come up with the desired end result. So as I said, it doesn't matter where you start or where you finish. We don't do the one directly, which is this equation. Instead, we go via 3 steps to get to the same end point, to get the end result. Okay, gang, that's all I have prepared for you today. I know it's tricky in 2 hours to summarize the whole course. I've tried to hit the highlights to remind you of the things that you should know as you prepare for the final exam. Again, if there are any questions, please don't hesitate to send me or Masood an email. We'll be happy to help in any way we can. It's been fun. I wish I could have seen you. I missed that interaction, but I hope it's been helpful. And thanks for signing on.
Thank you, Peter. Thank you, everybody, for participating. And again, we are going to have the rest, including organic chemistry, right? For the 9th of May, if I'm right. And so if you have covered organic chemistry in grade 11, you can join us also and just have the organic. But the rest are going to be specifically for grade 12. Definitely grade 12.
Yeah, basically the session in May will cover topics 6 to 10. Right, we'll start with kinetics and we'll end with organic.
Okay, great. Thank you. So thank you, Peter. Thank you, everybody, for participating, and we wish you good luck. And don't forget to tell your friends for the next one. Thank you. Bye now.